introduction. And yeah, I gave a talk yesterday, so I tried to orthogonalize the two a little bit. And of course, I'm going to give you more details today. And please interrupt me whenever you have questions. First, I'd like to acknowledge my collaborators, in particular at Argonne, the young people, Patrick Fasano and Anthony Dorviano and Bryce Ford. They're great. And none of this would have been possible without my friendship with Giuseppe Carleo in Switzerland at the PFL. The other collaborators include Noemi at Fermi Lab and Stefano at Los Alamos. Of course, Martin here, Jane, while she was here, now she's at Ohio. Mauro, who is now at CISA, it was at the University of Trento, and Francesco Vederivo, of course, a long time friend and collaborator. Probably this slide is superfluous here, but of course, we're interested in studying, in principle, as many nucleus as possible in the nuclear chart, because after it's going to deliver. Let me move a little bit this out of the way. Maybe here it's better. Right. And I want to say that these isotopes will provide extreme test cases to test both low and high resolution theories. So basically what you call the initial density function is really a different resolution scale. And ideally, we would like to achieve a consistent description of the structure of these nuclei and the reactions. Up to not a lot of progress has been made in this direction recently, but there is still some work to do, and I will try to explain you some research directions specifically towards achieving this goal with neural network quantum states. All right, but of course, nuclear physics is not just studying the nuclear chart. It has many implications. For example, oscillation parameters, neutrino physics, are studied using nuclei. The idea is that an intense beam of neutrinos is produced at Fermi Lab, which is comprised of basically just muonic neutrinos. And then it travels for hundreds of miles underground until it is eventually detected in South Dakota. And in the meantime, the shape of the flux has changed. And there are, for example, the neutrinos oscillate, and there are electron neutrinos contaminating the muonic flux. And the idea here is that from the product of the reaction, say protons, neutrons, and pions, one wants to reconstruct the unknown oscillated flux. And in order to successfully do this unfolding procedure, it is critical to know neutrino nucleus interaction with quantified uncertainties at really precisely at the percent level. In this paper with Vincenzo and Videk and other collaborators, we also highlighted how nuclear physics is crucial to test the very nature of neutrinos, so whether they are their own antiparticles. And here, computing with quantified uncertainties, the nuclear matrix element entering double beta decay amplitudes, it's critical to connect for designing experiments, for their sensitivity studies, but also if a decay is actually observed, to connect the lifetime with neutrino masses and parameters. And finally, nuclear physics is critical also for nuclear astrophysics. As an example, I'm showing here a pictorial representation of two coalescing neutron stars. And the idea here is, depending on the equation of state of neutron stars, so of matter comprising the interior of these compact objects, the signal detected on Earth by interferometer changes. Here I'm showing the tidal deformabilities of these two neutron stars, which basically tells us how stiff the equation of state is. Because if it is very soft, once they orbit, when they in spiraling phase, a lot of materials fall from one star into the other. If the equation of state is more stiff, then the amount of material is less. And that can be compared with the available equation of states to some confidence level. And this is the famous Akmal-Pandari-Van-der-Waavenen equation of state, which satisfies the astrophysical constraints. But with the next generations of telescopes, they're going to impose even tighter constraints on the equation of state. Now, a fundamental ingredient for attacking this problem is, of course, constructing realistic and accurate Hamiltonians and possibly consistent curvature. And these Hamiltonians are input to many-body methods, which attempt to solving the many-body Schrödinger equation, the quantum many-body problem with quantified uncertainty. And this by itself is a complicated task. And in fact, nuclear many-body methods are continually battling against the curse of dimensionality. So there's a typo here, which is the rapid growth with complexity of computational resources needed. Now, back to square one. Since nucleons are fermions, of course, the ground state wave function in Hartree-Fock, for example, is a Slater determinant of single particle orbitals. And these later determinants are tailored to the problem of interest. For example, if one wants to simulate infinite nucleonic matter, you want to respect periodic boundary conditions. If one wants to compute finite nuclei, say oxygen-16, you want to put your nucleons into, say, an harmonic oscillator basis or Wood-Saxon orbitals. And one can construct a basis for it, as experts in this room know better than I do. And this basis is, of course, complete. So one can expand the true ground state of the system, psi 0, in terms of one particle, one hole, or two particle, two hole excitations, and so on and so forth. Many particles, many holes. But the size of the Hilbert space grows with the binomial coefficient, because how many ways there are in total to put A particles in n states? Well, this is the binomial coefficient, which grows exponentially. This is what limits exact diagonalization techniques like the Noether model to fairly light nuclei, right? Because if you have many, many states, you can still bundle this by choosing a small a, so few nucleons, or you can choose to work in a smaller model space, small n, and put more nucleons in it. So it's a trade-off. And these calculations are excellent. I mean, I'm showing here some results that Chloe obtained for the astrophysical S factor. But I also want to mention that there are methods that somehow select the most important contributions in this Hilbert space. And now they can go up to LED 206. Examples of these methods are the medium similarity normalization group, the couple cluster methods, and the idea, or the self-consistent Green's function. So the idea here is to select the most, to use iterative solutions or diagrammatic methods that select the most important contributions out of this exponentially large model space. And on the other end of the spectrum, if you want, there are methods that are not based on single particle basis expansions, that they do not work on a finite basis. That can be the harmonic oscillator basis or the Wood-Saxon basis. And these methods belong to the family of continuum quantum Monte Carlo. And of course, a relative of this is the lattice Monte Carlo, lattice Monte Carlo that we mentioned later by Dean and collaborators. And the critical advantage of quantum Monte Carlo methods with respect to a single particle basis method is that they have no difficulties in dealing with nuclear forces that have high momentum components, high resolution nuclear forces. And the reason is that they typically work in coordinate space. And so they really have no difficulty in accessing physics happening at short distance. Whereas if you work in a harmonic oscillator basis, you need to use many, many oscillator quanta to resolve what's happening at short distance. And of course, there are workarounds to this problem. If one wants to work, use a low resolution wave function, one can perform unitary transformation in the operator and get similar results. And this is something we are doing with Anthony Dorgano, but I will not mention this talk. However, one of the key problems of quantum Monte Carlo methods is that so far they've been limited to light nuclear systems. And here I'm showing a typical conventional variational wave function. So continuum quantum Monte Carlo methods start from a variational wave function, which is a good approximation to the actual ground state of the system. And again, we start from a Hartree-Fock solution if you want, but then we operate on top of it with 2- and 3-body correlation operators. And the parameters, variational parameters defining these correlation functions are determined by minimizing the variational energy of the system. So it's a variational calculation. And the idea here, suppose that you have a 2-body potential with a strong repulsive core. If you work in a single particle representation, again, you need many, many oscillator quanta in order to model the fact that the probability of finding two particles close to each other is small. But a possible workaround, this dates back to Jastrow in the 50s, is to actually use a correlation function which is small when two particles are close to each other. So it's very close to 0. So that really reduces the probability of finding two particles close to each other. So it really encodes correlations. And this is typically the starting point of an imaginary time diffusion. So again, the idea here is that any variational state can be expanded in the basis of the variation of the Hamiltonian, psi n. And then by performing an evolution on imaginary time, only the ground state survives because energy is larger than the ground state one are suppressed exponentially. And this is shown in this plot for helium-4. So at larger imaginary time, excited state components are suppressed and we converge to the ground state energy of the system. And this is rigorously true for besides the sign problem. Like for bosons, this method is exact because the ground state wave function is nodeless. For fermions, the sign problem, which in nuclear physics becomes more complicated, emerges. And I will come back to this point later. But first, let me tell you why there is an exponential complexity in quantum Monte Carlo as well. The idea here is that when we do the imaginary time propagation, we sum over all possible many-body spin states, spin isospin states, but forget about the isospin. So imagine for a moment that we don't have protons and neutrons, but just neutrons. But neutrons do have spin, and the potential is spin-dependent. And so if we want to represent a many-body spin wave function for 3 particles, we have 8 amplitudes, because 3 particles can be all up, 2 up and 1 down, and so on and so forth. So it grows like 2 to the 8. So if you have 4 particles, it's 2 to the 4th, and so on, and so. And basically, then if you also consider the spin part, the isospin part, there is an additional binomial coefficient, which makes the problem exponentially harder and harder to solve. Okay? So this is why we're limited now to carbon 12 on Polaris and Aurora. We're going to reach 13 and 14. There is work done by Patrick Fasano at Argonne, but also by Lorenzo Andreoli and Anna McCoy at WashU. But yeah, I mean, we want to doing 14 and 13 is perfectly fine. There is a lot of interesting physics to do, but we want to, to go beyond that. Anyway, I wanted to show you some of the results that we obtained with conventional quantum Monte Carlo. Here is the, as I said, we can use these calculations to compute neutrino nucleus cross section, and this is an example of a parameter-free, if you want, calculation. We are computing here the inclusive cross section for a neutrino scattering of a carbon-12 nucleus. And now we can include one-body currents only. So basically, the Z boson or the W boson, this is a charge scattering, couples with 1 nucleon at a time. If we do that, we get the green. If we also consider processes in which we couple with pairs of nucleons, then we get the blue, which is in excellent agreement with experimental data. And more recently, we also did this for electrons. I mean, we computed the response years ago, but now we actually found a way to include the relativistic corrections because the momenta at play in this case is fairly large. It's of the order of 300, 400, 600 MeV. So relativistic corrections are critical. And so 1-body currents is the green, 2-body currents, 1 plus 2 is the black. But we miss the quasi-elastic peak because of relativistic corrections. If one includes relativistic corrections, we can get the blue, which is in much better agreement with experimental data. So it's critical, again, if one wants to apply this method to neutrino oscillation experiments to validate it first on electrons. But now let's dive a little bit into this exponential complexity, okay? So the first, we said the many-body spin basis explodes exponentially, and so does the coordinate space, right? But we don't care about the problem. I mean, we typically we use some Monte Carlo sampling to sample the coordinates of the nucleons. So we don't care about the exponentially growing problem of using like the Simpson rule, for example, of integrating over the spatial coordinates of the nucleons. We sample them. Can we try to do the same with the spin? The answer is yes. And for example, instead of working in a many-body spin basis, one can work in a single particle spin as a spin representation. So basically, the spin coordinate is really the tensor product of the single particle spinors. And each single particle spinor is a linear superposition of proton up, proton down, neutron up, neutron down. So instead of having 2 to the A coordinates for the spin, you would only have 2 times A coordinates. But of course, by doing that, we neglect entanglement altogether. An entangled state cannot be written like this, right? And how does this show up? Suppose that we pick one state in the Hilbert space, and we apply this correlation operator, which is known to entangle, like sigma 1 dot sigma 2. This is the same operator entering the potential. This can be written as twice the exchange minus 1. So if we apply, forget about the isospin, but if we apply this operator to this state, which is state for particle 1 times state for particle 2 times state for particle 3, we get twice a state in which we exchanged particle 1 and 2 minus the original state. Now, this linear combination of 2 tensor products cannot be written as a single one. So basically, imagine to do an imaginary time diffusion starting from this state. At the very first time step, you get 2. Then you get 4, 8. So they explode exponentially again. How do we keep this under control? We use Abbas atomic transformation. But the other problem is that we cannot use the same variational wave function used in variational Monte Carlo methods. We need to use simplified wave functions because applying this product of spin operators, again, scales exponentially, even if you sample the spin. So the idea is that sampling the spin alone doesn't solve the exponentially scaling problem of Green's function Monte Carlo. You also need to devise a wave function that doesn't scale exponentially with the number of particles. So there are two critical components, always. Sampling the Hilbert space and writing a wave function that scales polynomially with the number of particles. So a workaround to this problem was to linearize the spin correlations, and Diego and Stefano picked up this idea and computed nuclei up to oxygen 16, even larger, a little bit larger now with chiral-FT interactions, obtaining beautiful agreement with experimental data. But the problem with these ansatz is that it violates the factorization theorem. So basically, suppose that you have a large nucleus, a large system, and then you want to separate two subsystems and you put them far away from each other. You want the wave function to factorize. It's a theorem of quantum mechanics. And this clearly violates. So this one is fine. The product is fine, but as soon as you linearize it, you violate factorization. So you immediately realize that this ansatz is not good. You cannot use this ansatz to describe nuclei much larger than oxygen 6. Nevertheless, I just wanted to flash you this result, which we recently obtained in neutron matter using the auxiliary field diffusion Monte Carlo. So sampling the spin and using a simplified wave function. Neutron matter is easier because operator correlations are much weaker. And there I'm showing results if no three-body force is included. And if an attractive three-body force instead is used, we get these unphysical clusters of neutrons that are tightly packed. So again, quantum Monte Carlo here fairly easily gets to this situation in which there are strongly packed, unphysical case in which there are strongly packed clusters of neutrons that immediately tells us that we cannot have an attractive three-neutron force in neutron matter. But achieving such a clustering with an harmonic oscillator with any basis expansion will take a lot of effort, right? So there is something good in quantum Monte Carlo methods. We want to try to exploit it. But this is somehow the pictorial representation that we have. So the Green's function Monte Carlo scales exponentially with the number of particles. The auxiliary field diffusion Monte Carlo scales polynomially, but it's extremely noisy as soon as you get beyond oxygen 16, just because your wave function is not accurate enough. And we know that we have to tackle the fermion sign problem. And having an accurate wave function is critical to control it. So that was the puzzle we were. This is why there are no auxiliary field diffusion Monte Carlo calculations of large nuclei, despite in principle the method scales fairly. All right, so back during COVID time, we actually started playing with it as a game, because Giuseppe Carleo introduced this method to solve spin systems, and we thought, okay, what if it works for nuclei? It would be probably a game changer, but we didn't know back then. So we just tried it since we had time. Anyway, this is the main representation. So the idea is that the Hilbert space does scale exponentially with the number of particles, but not all of the possible states are of physical interest. I mean, we know that mean field calculations, for example, do an incredibly good job in describing properties of nuclei across the nuclear chart. Even the shell model, it only captures a tiny region of the Hilbert space. The mean field is actually optimized because you pick the right single particle orbitals, and that's a critical point for link success, I believe. But anyway, the thing is that the hope is that the set of physical states is much smaller than the full Hilbert space. And this is how neural network quantum states work in a nutshell. The idea here is that we use artificial neural network to really represent the quantum mechanical state. So for us, a neural network is really takes as input the coordinates in the Hilbert space. For example, they can be the positions of the nucleons, x, y, z for each nucleon, and their spin. Or in the cohesion number formalism, can be a string of 1 and 0s, depending whether the state is occupied or not. And the output is the actual wave function. So it's a complex number. Now, these parameters at the beginning are completely random, like in most neural network applications. And the idea here is to train this net by minimizing the energy. So for a given Hamiltonian, we minimize the energy with some fancy methods. And then we get an artificial neural network that closely resembles the ground state of the system. So nets here are not used to extrapolate observables we are really opening the box and trying to use the net to represent the quantum state. And this was introduced by Giuseppe Carleo, sorry, I missed the reference here, Matthias Streuer in 2017. in spin systems. So they showed that using such an ansatz improves dramatically with respect to simple just row ansatz for the Ising model, for example. But then, as I said, you need two ingredients. One is a wave function that scales polynomially with the system size, and the other is sampling the Hilbert space, because the Hilbert space is going to be exponentially large. And so we typically do that with Metropolis Hastings algorithm. So we really compute the energy of the system by sampling the Hilbert space with the modulus square of the wave function, and then compute local observables. And computing, since the Hamiltonian is, contains at most 2 or 3 body terms, this is polynomial cost to compute. So there are, again, these two main ingredients.
So for your question,
sure.
The P.
P is the set of parameters of the net. Okay. So you can think of them as the weights, the biases, and so your answer, of course, depends on the weights. So if you change the weights, your wave function is going to be different. Then we optimize the weight by minimizing this expectation value. It's really a variational Monte Carlo. Yes.
So, this wave function was just the numbers in the numbers in your space, or it's it's not some power.
No, I will show you later the exact structure of the wave function. How it is done. Other questions? Okay. And this is a picture by Jenkins that I really like. So if the Hilbert space is really like that, there is no hope that this is going to work. Okay, so if there is no structure whatsoever, this is doomed to fail. But what if there is some structure? We know there is. Then there is hope that this method is going to work. It is not guaranteed, but it is possible. It is plausible. And we know that mean field works. This is critical. I mean, if mean field didn't work, we would have had way, lower expectations in a sense. Anyway, there are two, to answer a little bit your questions, there are two big families of neural quantum states for fermionic systems. For bosonic systems, the situation is it's much easier. But it's harmonic. I don't know why it's harmonic. But the fermionic anti-symmetry is telling us if you exchange particles psi and j, we need to get a minus sign. And now there are two ways to do that. One is to work in real space. So the net takes as input, for example, the positions of the particles, but it doesn't have to be. It could be, you could do this in momentum space. But the thing is that this wave function has to be anti-symmetric if one exchanges particles I and j. So the first answer is a Slater Jastrow, meaning that this e to the u is a Jastrow factor, which is symmetric under the exchange of two particles, and phi instead is anti-symmetric. This is very powerful, but it is not universal. So there are functions that you cannot represent this way. Ferminet and Paulinet, so Google and other groups, introduced backflow Jastrow. So basically here the idea is that in the Slater determinant, you don't use the original coordinates of the particles, but you transform them. I will come back to this point later. And this is actually universal. One can show that any anti-symmetric wave function can be written in this way. But the third family is the hidden fermions. So the idea here is to extend the Hilbert space. I will come back to this point later on. But the message here is that if you work in real space, then you need to encode the anti-symmetry into the wave function. Because if you don't do that, you collapse to the bosonic state, which is always the ground state of the Hamiltonian. Or the other possibility is to work in the occupation number formalism. So map the Fermion Hamiltonian into a spin one, like typically done in quantum information science. You can use Jordan-Wigner transformation or any other transformation that you can think of. And then you solve the spin problem with feed-forward neural network. So basically, in that case, the input is a string of 1 and zeros. 1 if the state is occupied, 0 if the state is not occupied. I showed this yesterday a little bit. So today I'm not going to focus on this part. I will really dive into the details of the first. But if you have questions on the second, I'm happy to answer them. All right, so the first actual study of nuclear systems with neural quantum states was done by James Keeble and Arnaud Rios at the University of Surrey, and they solved the deuteron using Canali effective field theory interactions, but they didn't use variational Monte Carlo to sample the Hilbert space, so they actually used a grid. We wanted to treat larger systems, and of course we pretend we know quantum Monte Carlo, and so we said, okay, let's try to combine the two. And to begin with, we started from a simpler pi-inverse effective field theory Hamiltonian, which is basically a Gaussian potential once you regularize it. But it contains a two-body force, which has a spin and isospin term. So solving it with the GFMC will still scale exponentially, and the auxiliary field has a sign problem, and a three-body force. And these are fixed to reproduce the effective range and the scattering length at the two-body force in the two-body system with some caveats. And the three-body force instead is fit on, say, Triton and another observable mean. In our first work, we used the Slater-Jastrow approach because it was the simplest thing to do and we were familiar with it. So bear with me. So the answer is the following: as Slater-Jastrow. Forget about this tan H. We found out later that that wasn't essential, but back then we thought we had a great idea, but it's really not essential. The idea here is that we have e to the u, which is a real function, times a Slater determinant. And the mean field part, at the beginning we were naive, so we thought, okay, let's write it as a single Slater determinant or a sum of Slater determinants, depending on whether the nucleus is open or closed. And these single particle orbitals were simple feed-forward neural network, and we eliminate center of mass contributions by just removing the center of mass coordinate of the system. So again, here there is no shell structure whatsoever. So there is no spherical harmonics, nothing. Everything is completely learnable. It's a net, which is initialized randomly. And this, of course, is anti-symmetric by construction, right? Because if you exchange particle I and j, you get a minus sign coming from here. And then the whole thing is anti-symmetric if this is symmetric or permutation invariant. And doing it by hand, of course, costs factorially, right? Because suppose that you have three particles, 1, 2, 3, then you want to symmetrize the whole thing. It's like a permanent, and it costs a factorially large number of operations. Fortunately, there is a theorem which goes under the name of deep sets. And the idea is that any permutation invariant function f can be sum decomposed. So here, the idea is really to start from the original coordinates of the nucleons, say x, y, z, the spin projection and the isospin projection, so 5 coordinates for each nucleon. Apply the same net phi to all of them, and then apply an operator like the sum that destroys the ordering. So once you apply the sum, this thing does no longer depend upon the ordering of the nucleons. Then we apply another network rho that takes us from this latent space to a to a real number. And one can show actually that any permutation invariant function can be sum decomposed. And this is really powerful because it tells us that this approximation is universal. And this is what we actually do. In a less naive way, but this works. If you try, it works. And now this is related to simplifying in vector continuation, even though it's completely independent. It was invented by Sandro Sorella in 2001. And there is an analogous in neural network which goes under the name of natural gradient. And the idea here is that we don't really just minimize the energy naively. We don't just compute the derivative of the energy. That wouldn't work well. What we really do, we work on in the wave function. So here, suppose that one applies the first order imaginary type. This is like a power meter. Or if you can think of it as a throttle expansion of e to the minus h delta tau to the original wave function. We have a set of parameters p of tau, and we apply 1 minus h delta tau. If we apply this thing many, many times, we converge to the ground state, pretty much as we do in diffusion Monte Carlo. But here, the idea is that we approximate this function, which is obtained by applying 1 minus h delta tau to the original one, with a wave function with parameters changed, with a network in which we change the parameters. And how do we find these parameters? Well, we maximize the fidelity between the quantum fidelity between these two states. So this is the expression. So it's psi bar is this thing here, and then if they are the same, this ratio is 1. If they're different, this is smaller than 1. So if we maximize the fidelity, we basically solve the problem. And this can be done either directly, so we can actually maximize this thing, or one can do a linear expansion around, assuming that p tau plus delta tau is close to p of tau, one can do a linear expansion. And this is how the update looks like. So the new parameters are the old one minus delta tau. I don't know why I wrote eta. We should change this. And then this is the gradient of the energy, but it has to be multiplied by this quantum Fisher information matrix. So if one just minimizes the energy, you get just the gradient. But by doing this, you get this matrix S, which is the quantum Fisher information matrix, which basically tells us how different two-wave functions are. If two-wave functions only differ by a multiplicative factor, a common phase or a common constant, they're actually the same. So two parameters can change a lot, but give you exactly the same wave function. So if you want the right metric in the Hilbert space, it's not the Euclidean metric. So if you want to measure the distance between two wave functions, the distance is not really the Euclidean distance, the distance between the parameters, it's really the overlap. And this accounts for that, and it makes a huge difference. So when we apply this to the deuteron, we try two different, pretty stiff timeless effective field theory interactions, and we converge to the exact ground state, which we can compute in a few hundred steps. And this was done in 2020. And but then we said, okay, let's study in the same level. We studied slightly larger nuclei, which is Triton and helium-4. And yeah, so with a conventional variational Monte Carlo calculation, we improve upon that. So we get, say, from minus 7.8, we got minus 8.26, but we were missing a little bit to get to the exact answer, the Green's function, the numerically exact answer. And the reason was that the differences were due to deficiencies in the Slater-Jastrow ansatz. So we cannot really represent any anti-symmetric wave function in this way, right? Because if this phi has a 0, there is nothing this exponential can do to correct for it, right? So are we back to the sign problem? Okay. Yes. The answer is yes. So in fact, one can show that if you start from the same phi in diffusion Monte Carlo and with neural network quantum states, you get to the same fixed node answer if your Jastrow is flexible enough. And we showed that later. I'll come back to this point. But we wanted to overcome this difficulty. So now think of the helium-4, a simple nucleus. You have 4 single particle orbitals, phi 1, phi 2, phi 3, and oh, you have questions. I mean, stop me if you. I don't want to lose you that early. Okay. Anyway, there are 4 single particle orbitals. This is very for you that you were trained as nuclear physics. Some of you think are trained as nuclear physics. It's easy. I was not, and so when everything was a discovery for me back then. Not back in 2020, but back then. Anyway, this is a single Slater determinant, which is fine. But then what if we add hidden degrees of freedom? So the idea here is that, yeah, there are visible orbitals on visible coordinates, but we can artificially enlarge the Hilbert space, adding hidden degrees of freedom. This y1 are the coordinates of it. We can think of them as additional particles that do not really exist, but are there. But of course, to make the whole thing antisymmetric, we need to add additional states, single particle states, this kind. And so, yeah, we have visible orbitals on visible coordinates. This is the Hartley-Fock approximation, if you want. Then we can add hidden orbitals on hidden coordinates, but then we have hidden orbitals, this chi on the visible coordinates, and visible orbitals on the hidden coordinates. Now, if you take just one hidden nucleon, so just this part, and then you set this to 0, say, and this to 0, we recover this Slater-Jastrow ansatz, right? Because it's a determinant multiplied by this factor. Ah, sorry, I forgot to say one thing. This works if these y are permutation invariant functions of x. So if you exchange x1 and x2, the y is unchanged. Okay, so if you exchange, say, x1 and x2, we exchange these two columns, and nothing changes here, so we get an overall minus sign when we compute the determinant. So this thing is antisymmetric, which is good. Then, again, if we set this, if we just had one hidden and only this different from 0, we recover this later times the Jastrow. So we recover the Slater-Jastrow as a specific case of the hidden. But then one can show on the lattice, in the continuum, there is no proof that this is actually universal. It's a universal approximation for antisymmetric functions. So it allows us to go beyond the fixed node approximation. All right, so this is the pictorial representation, right? So if we have 3 nucleons that are very correlated, say, but then we can map this problem into a larger Hilbert space in which we add additional fictitious degrees of freedoms. But now they are kind of the mediators of the interaction. And so the correlations among the initial nucleons are way, way weaker. So the idea really is that a single Slater determinant for this whole system is fine. Okay? All right. Questions? No. Okay. All right, so we tested it on oxygen 16 and adding more and more hidden degrees of freedom, comparing with the conventional variational Monte Carlo ansatz and the auxiliary field diffusion Monte Carlo, which again is not exact because it suffers from the Fermi sign problem. But anyway, we were happy because we got good agreement with it, not only in the energy, but also in the single particle density. Now, the trial state in the auxiliary field diffusion Monte Carlo calculations, so this orange, is basically a Slater determinant of Wood-Saxon orbitals. So if you want, the shell structure of the system is encoded in the problem. It's like using a reference state in post-Hartree-Fock middles. Here, instead, everything is learned. So the blue points are learned. So there is nothing, no information whatsoever on a confining potential, nothing in the net. So the net not only learns correlations, but it also learns single particle features of the nucleus. So there is no reference state, if you want. Everything is learned from scratch, which I think it's it has an intrinsic beauty, right? Because the only input to these many-body methods are the Hamiltonian, the number of protons, and the number of neutrons. In this case, also the number of spin up and spin down, because the pioneer CFT interaction doesn't have a tensor, but everything else is prediction. And then we went on and we said, okay, we can do nuclei, we can do neutron matter, and especially low-density neutron matter, because with a pioneerless effective field theory interaction, we don't want to tackle the high-density region, because we know that the Fermi momentum is too high for a pioneerless CFT to converge there. So we said, okay, let's compute the energy per particle. This is the neural quantum state. This is work done by Bryce for at Argonne postdoc. And this is how the training works. So the energy decreases, and then agrees very well with auxiliary field diffusion Monte Carlo unconstrained propagation. So we need to basically lift the constraint on the phase of the wave function, which is principally numerically exact. But to get it, we need to use millions of core hours. Whereas with the neural quantum state, a few 100 GPU hours are enough. If one does a cheap constrained path auxiliary field diffusion, Monte Carlo gets this biased result. Okay, so for us, we were really surprised that it really works. And not only we compute not only the energy, but also two-body correlation distribution functions. And here I'm showing the spin triplet versus the spin singlet. And we know that there is pairing in neutron matter. So the idea is that really this should be reflected in the two-body distribution functions. There are other indicators of pairing that we computed but not showed in the paper. But anyway, the triplet is basically unchanged compared to the Fermi gas, to the uncorrelated case, the Hartree Fock. Whereas there is a huge bump in the singlet, because pairing is basically in the singlet channel, right? You want the opposite spins. And this difference decreases if we increase the density. So at very low density, there is more pairing. And also, that was really surprising to us, but I'll come back to this point later. We compare this simple low resolution, pioneerless effective field theory interaction with highly sophisticated Hamiltonians, like the Argonne D18 and different chiral effective field theory potentials by Maria Perulli and collaborators. And all of them, Argonne D18 and chiral effective field theory forces, they basically give this green band at low density, because they're basically constrained by the scattering length and the effective range. And so we said, okay, what if we use our pioneerless CFT, which is constrained to reproduce, again, the scattering length and the effective range, we get the blue. A different pioneerless CFT interaction, which is only constrained to reproduce the scattering length, no effective range, gives us the orange. So it seems like both of them are important in the low density regime, unless we go to very, very low density. In that case, it's universal and only the scattering length matter. But it was a kind of surprising to us that such a simple interaction could capture the equation of state of neutron matter obtained with more sophisticated potentials. Anyway, let me take a condensed matter detour now, because we talked about superfluidity. Let's try to understand a little bit more what's going on. And this is work done primarily by Jane, that was a student here, so you know her very well, and probably you saw this slide already. But anyway, we're interested in describing cold Fermi gases with tunable potential. And basically, depending on the strength of the interaction, we can either have a BCS space in which the correlations is very long range, and we have pairing. Then at the unitary limit, the scattering length diverges, and this problem is extremely hard to solve. But then if we further increase the strength of the potential, really these fermions form pairs, molecules. Like, so the potential is attractive between up and down, and it's zero between up, up, and down, down. So what we form are really molecules, tightly packed molecules of up and down particles. And there's a first order phase transition between these phases. And we modeled this problem using a Posh-Teller potential with tunable with 0 and mu. Okay, the idea in the unitary limit is the effective range is 0 and the scattering length is infinite. Now we consider different ansatz. that has to be periodic, okay? So we are dealing with a periodic system, so we need to map the coordinates into the periodic one, but this is a technicality, don't focus there. First, we considered again our famous Slater-Jastrow ansatz, in which we have a Slater determinant times a Jastrow factor. Both of them are neural networks. And in this case, we know, because of the symmetry of the systems, that single particle orbitals are plane waves. And then, since we consider spin in our Hilbert space, there is also a product of the spin in the Hilbert space, Sj versus sigma, the state. So basically, these are plane waves with a given spin orientation, the single particle state. And then we can improve upon the nodal structure of these ansatz by doing a backflow transformation. So the idea here is to replace single particle orbitals with orbitals, the same orbitals, but computed in a different coordinate. Okay? And this is, we thought it was universal. And we still think it is, but it's very hard to learn. I'll come back to this point. As a second ansatz, we consider the so-called Pfaffian. So here the idea is basically a number projected BCS wave function. And again, the idea is that we replace single particle orbitals with pair orbitals. And each of these orbitals are anti-symmetric. So if you exchange particles I and j, we need to get a minus sign. And we do this by parameterizing these orbitals with a net. And basically we impose anti-symmetry by construction. And as an example of the Pfaffian, I'm showing you the 4-particle case. The idea is really partitioning. So you can imagine to have 4 particles and then compute all possible arranges in 2 subsets. So you have 2 partitions containing 2 particles each. And then these are the possible, each partition is anti-symmetric, and then you need to anti-symmetrize the partitions. And one can show that computing these things scales like the Slater determinant, 10 to the cube. But it contains pairing, and you can recover the Slater determinant with a particular choice of phi. So it contains the Slater determinant as a specific case. It is more general. And remember, though, that there is only one orbital for the whole system. So this phi is only one. In the Slater determinant, remember, we had as many orbitals as states. In this case, the critical difference is that there is only one phi. Okay, so this network doesn't, the computation of the cost of computing the net scales with the number of particles, like n to the cube, but the size of the network itself, it's fixed. It doesn't scale with the number of particles. Okay, which is it's a critical difference compared to other architectures. And then this was an idea by the EPFL group, but Jane perfected it. We use, I don't want to go into the details, but the idea is that we use a message passing architecture to build correlations into the single particle orbitals. I say that we do backflow transformation, so we don't compute the Slater determinant or the Pfaffian in the original coordinates, but we use a neural network to map the original coordinates into the new ones, this H. And the physical motivation behind it is that, yeah, the system is again very correlated if you look at the original Hilbert space, but then you can do a transformation and use a different even dimension. So you can go from a 3-dimensional space to a 20-dimensional space, and in that space, correlations are basically 0. You can solve your problem with the Slater determinant. If you want, the analogy that I have in mind is with the normalizing flow. Right, in that case, you have a very complicated distribution in the original space, but then you can do a normalized flow and then have a very simple distribution to learn. The critical difference that we haven't published, but we were studying it, is the Jacobian. So in the normalizing flow, you need a particular choice of the Jacobian because you want to conserve the probability. Here, instead, we wanted to show that with a phase transition, the Jacobian becomes ill-defined, but we didn't really manage to show it. If you can show it, it would be great. But anyway, we failed. But that was our idea, and I think it kind of works, but I don't have proof, so I'm not going to show it. But what I'm going to show is a comparison that again worked by Jane primarily between the Slater-Jastrow and the Pfaffian-Jastrow ansatz. First thing, sanity check. We can do a diffusion Monte Carlo calculation starting from plane wave orbitals. Now, if the Jastrow is universal, so if our net is big enough, we have to reproduce this result. And this is what happens. So the blue is what we obtain by increasing the size of the message passing neural network, the depth of the message passing neural network. And then if we make it large enough, we match diffusion Monte Carlo results starting from the same single particle orbitals. So this tells us that this network is general enough to reproduce diffusion Monte Carlo, fixed node diffusion Monte Carlo calculations. Now we can say, okay, but there are diffusion Monte Carlo for these systems are typically done using a Pfaffian ansatz like this. not using neural network, but specific parameterizations for phi, and they get the solid line. So we thought, okay, if we do backflow, if backflow is really universal, as it should be, we should get to the solid by just adding backflow to the Slater cluster. And we didn't get it, the orange, and we still don't understand why. We think that it has to do with the learning. So it's a transformation which is extremely hard to learn. So mapping, and it could have a diverging Jacobian. But this is speculative, okay? And Google DeepMind found exactly the same issue. We worked on this topic independently together and published our paper like a week apart or something. And the solution for us was to use the Fathian. And if we do that, we get the green, which is better than state-of-the-art diffusion Monte Carlo calculation. Yes. This is only 14. I'm going to show results with more. But this is only 14 particles. Okay, so a tiny system. It was a hard toy problem. Okay, but it showed us really the limitations of these answers, which are, I have the proof that this is universal, but it doesn't work. So I'm happy to discuss this with you. Anyway, what we did and Jane did actually was to use different effective range. So the idea is that we need to extrapolate to zero effective range. This is comparing ours, orange with diffusion Monte Carlo, they're consistently below it. And Vita here asked a question, which is, why don't we reproduce the Birch parameter? So the idea here is that at vanishing effective range, the only scale, at infinite scattering length, sorry, the only scale in the system is the Fermi energy. So the energy of the system should be proportional to it. And the constant is a kind of, it can be computed exactly with lattice methods. I don't know if Shuai-Zhang computed them. I don't know if you computed them too, but that can be computed exactly for this kind of systems, and we don't get it. And the reason is that we're only using 14 particles here. And the referee asked, yeah, okay, it can be accepted if you do more particles. And we realized that we can do on a single GPU node up to 32. And then on Polaris, we can do like on the up to hundreds or more. But anyway, this should be enough. And again, if we compare with diffusion Monte Carlo, we do better. And we are getting closer to the Birch parameter. But here, this is fixed effective range, which I believe is this. So we still need to extrapolate to zero effective range. So we need to do both things. But it's possible. At this point here, we didn't want to show that we could do the exact calculation, which we can do, but just to show that a different answer. Anyway, questions? Okay, let me go back to nuclear physics. I'm finding these pictures on the web. I should put the credit here, but I forgot, sorry. Yeah, so the idea is that, okay, we can use the same ansatz to do neutron matter. And in fact, we can do asymmetric matter. So adding protons to the 14 neutrons. And in that case, we should see clustering. So the formation of helium-4 or the deuteron, right? And this is what happens in the crust of neutron stars. And Dia has done beautiful work on this. And it was really inspiring for us. And yeah, so here we are comparing again artifact approximation with auxiliary field diffusion Monte Carlo. In this case, the fixed node approximation is so bad because we start from plane waves. And if there is clustering, the nodal surface is going to be very different. And the neural network captures it. So we go much below, this is energy per particle, okay? So we go way below the state-of-the-art auxiliary field. And these are the possible configurations, right? We could have a liquid phase in which the two neutrons, there are 14 neutrons and 2 protons. The 2 protons can float around, and this is a liquid. We can have 2 deuterons, or we can have helium-4. And Dean and collaborators have done a beautiful work on this, calling this tilting clustering, I think. We aren't there yet. What I can show you is the two-body distribution function. So if the phase is liquid, basically, sorry, if the phase is liquid, you don't see any proton-proton bump, you don't see any neutron-proton bump, they're washed out. If there are 2 deuterons, what you see a bump in the neutron-proton case, but not in the proton-proton case, because these 2 deuterons can float around. So the protons are not really close to each other. If there is a helium-4, then you see a bump in the proton-proton distribution too, and this is what happens. It's magnified by factor 10 because of normalization issues. This is still working on the best way of showing these results, and I'm talking with Dean about clever ways of showing it. But we do see a signature of clustering. And we can only do 0 temperature for now. Dean has done also finite temperature, but I think it's a start. And in fact, I wanted to show this paper here because it's really good. And then we went on, we said, okay, let's do symmetric matter, 14 neutrons and 14 protons, again at low density. In this case, we should see oxygen-16 forming and possibly other nuclei. Well, again, I mean, we don't have, I mean, I can show you again the two-body distribution functions, but in that case, they're not going to tell us whether we have helium-4 or oxygen. So we are still trying to figure out a way on how to show what kind of cluster it is forming. But what I can tell you is that, again, the neural network outperforms the auxiliary field diffusion Monte Carlo by a lot. It's like 2 MeV per particle. It's really a lot. And the reason is that, again, the auxiliary field doesn't have any information on clustering. So if clustering is really important, and within a fixed node approximation starting from plane waves, you cannot see it. And this is work done again with Bryce. Now let's go back to nuclei. Now that we learned, it's really a learning process for us, not just for the net. So we learned that adding using this message passing neural network is critical. And thanks to Jane, Gabriel, and the DFL, we learned this. And we say, okay, can we go back and apply it to nuclei? So to hit them with backflow, so that combine the two things. And the answer is yes. And this is again oxygen-16 with the same potential as before. So these are the previous data, adding more hidden. But if we pre-process the coordinates with the hidden, with the message passing, we get already with one hidden Fermi, we get a dramatic improvement. And this is, now the next thing to do would be to do an unconstrained imaginary line propagation in the auxiliary field to see if we can really get down to here. So here, probably adding, I don't know, 200 hidden, we would get to the same point. But, this combination appears to be extremely effective. And so basically we used it. And again, this method is variational. So we know for sure that the real energy is below the green. Okay? And so, yeah, again, I mean, I'm quoting again this led us to actually study what the essential elements of nuclear binding are. So we copied a little bit this title, this paper by Dean, but we were also inspired by this work that we did like a few years after that, in which we used a very simple pi-less effective field theory inspired interactions, which again, we fit the two-body interaction to the scattering length and the effective range of neutron-proton and proton-proton system. And yeah, sorry, neutron-proton, sorry, not always neutron-proton, but the T equals 0, S equals 1, and T equals 1, S equals 0 channel, and the three-body force to reproduce triton and say helium-4. And so we asked ourselves, okay, how does it do with large nuclei? And the thing is that we can choose a regulator in the three-body force, so we can walk, if you want, on the line of the binding energy of triton, and that gives us connects the cutoff and the coupling of the three-body force. We can walk on this line and say, fit, I don't know, helium-4 exactly, or oxygen-16 exactly, and then we can compute all the other nuclei. And here I'm showing the energy per particle of all nuclei that are bound for us. For example, helium-6 is not bound with respect to the breakup in helium-4 and 2 neutrons. And I'm talking with Vitek about and Dinos about how to solve this, because it should be bound, but it's a fine-tuning process. But anyway, the message here is that I think the agreement is remarkably good, is within a few percent compared to experimental energies, and this is confirms what Dean had found before. And the other thing is that we can do open shell system or closed shell system without difficulties. And again, using better wave functions, we could improve this energy a little bit, but I don't expect to be able to reach the experimental value. Now, more recently, we did silicon 34 and sulfur 36 because we wanted to see bubble nuclei. And this is preliminary. But we are very close again to experimental data, but I'm not showing the densities because it's still work in progress. So, and I mean, we know. Yes, I don't want to comment too much on this, but I think it's good that we can go up to this region and we can actually do calcium 40 and 48 as well. And in addition to binding energies, we can compute radii. And here the situation is, so we had no difficulties. We believe our wave function is flexible enough that we don't have problems like working in the harmonic oscillator basis with the wrong boundary asymptotic behavior. This is like after-fall calculations in a sense, where the single particle orbitals are learned in a sense. Like in after-fall, you learn them by solving the Schrödinger equation. Here we learn them and utilizing the energy. We don't work in a basis. But we overpredict the radii of some nuclei, we underpredict some of them. And this is consistent with the binding energy in a sense, because we underbind this kind of nuclei. But I mean, the trend is okay, but there are significant differences, okay? And so once again, radii seems to be more sensible, more informative than binding energies alone to the quality of the nuclear process. And the other last thing that I like this thing a lot because it's related to responses, if you want. The idea is that, okay, we're using a higher, less effective field theory interaction with no tensor, okay? So our ground state is going to be degenerate in LZ and SZ. So the spin projection of the angular momentum and the spin projection. Now we can fix FT in the metropolis walk. So we can fix the total spin of the system. But then somehow, in order to compute the magnetic moment, we want to use maximal JZ projection because this is how they are defined. But the net can end up in any possible linear combination of these states because it's degenerate. They all have the same energy. So there is no way that minimizing the energy can tell what the LZ is. And so what we did, we actually removed the degeneracy by applying an external field. It's not really a magnetic field because it only couples to LZ. But the idea is that by adding this thing, we could polarize the nucleus. And this is what actually happens. So this is, right, I think it was vegan 7. Anyway, the idea is that at the beginning, the magnetic, let's go for first JZ. So at the beginning, we have a random JZ basically. But then by turning on the field, this increases JZ. Okay, then we switch it off, and then it converges to the desired value. And the same happens with J. So the actual value for that nucleus is this one, but we end up, for the maximal JZ projection, but we end up in a linear combination of them. But adding this external field removes the spurious contribution. So it's really related to the spin response, to the response of the nucleus, right? Because our wave function is in a random angular momentum state, but then we can cover with a field and field, which is, I think, interesting in its own, and it opens the way of computing response. Yeah, but anyway, these allowed us to compute magnetic moments, and I'm comparing here with some results from Stefano Mendorfi and collaborators in Los Alamos, and we agree fairly well, we agree very well with experimental data, except for helium-3 and Triton, because of two-body currents missing. And also, yeah, this is obvious, right? I mean, if you did a shell model calculation, this would, or our density function calculation, they will come up right away. But for us, we really wanted to show that we have self-emerging shell structure. So if you don't have the right shells, you don't get this right. But since we don't put shell information into the wave function, we wanted to test that we have the right one, the right angular momentum and everything, and we do. Which is, I think, another indication that this is working. Finally, some conclusions is that, yeah, this variation of Monte Carlo with neural network quantum states is, by design, scalable to leadership class computers. We can scale to the full Polaris machine with almost ideal efficiency, and we can go up to germanium 76, but it's really a stretch. So for us, like the ballpark now is up to calcium 48. On Aurora, instead, we would probably be able to reach the thin region. And these are some developments. So the tensor force is critical to explain many aspects of nuclear structure, especially shorter range dynamics. And the inclusion requires changing the metropolis algorithms, because basically now we preserve the total spin projection, and tensor breaks it. So we're working with Anthony Troviano and Bryce Ford on that. And then we want real-time dynamics. This is the prototypal exponentially hard problem in many-body theory, which is relevant for fission, fusion, lepton, and other nucleus scattering. And here the idea is similar to what we do in the optimization. It's really to minimize the distance between the real-time evolved state and an updated neural network. So minimize this thing because there is an arc cosinus. But anyway, maximize the fidelity. And this is, I mean, we can learn a lot from time-dependent artifact. I mean, we don't have to reinvent the wheel. Here, collaboration with Kyle and Hilbert. Really appreciate it. And then there is an alternative approach based on integral transform, and basically on neural Lorentz integral transform if you want. And this is collaboration with Nir, a student of his in London. Finally, the last slide, some perspective is the larger nuclei will enrich. So with Corey Adams, he can already reach germanium 76 on Polaris using the full machine. And he works at ALCF, so that's why he can do that. I would use my own allocation very soon if I did that. So work is in progress to part it to Intel Ponte Vecchio, because it's the Aurora Intel card, and Corey is working on that. And then yesterday I mentioned the occupation number formalism, and in this case we're working with Patrick, Mauro, and I'm happy to talk with you about that more. And this is all. Thank you.
Guess we haven't taken away the audio slide here. Any more questions? Any questions?
It's really, I feel like that's part of this. It's very interesting ideas. The question is, do you see a lot of dependence on the actual force, the short range force when you do the machine learning?
That's so the hardest thing we try. Okay, so at the very beginning we tried high-endless CFT with very high value of the regulator. Like that was harder than Argonne, I think, the 18. And yes, so it was harder to learn, but then with message passing, neural network becomes much easier. And we can always do transfer learning. So we can train the net first on a softer interaction and then use it as a starting point for a harder one, like Jane did in the cold atoms case. And that worked very well. I mean, cold atoms, it's really extreme because it's short distance and super deep. Nuclear forces are fortunately less. But yeah, but it's in general it's more difficult. But with
Question?
So I just have one question. During the talk, you would have this notion of universality. Could you explain what that is? How you would know?
so I think I said universal in the context of cold Fermi, of unitary Fermi gas, cold Fermi gases at the unitary limit. They're universal in the sense that if you take this interaction, say, and then you take the scattering length to infinity and the effective range to 0, there is basically nothing depends on the scale of your system. There is only the only scale is the Fermi gas, the density. Okay, and these are universal in the sense that if you are in this regime for physics, say neutron matter at very low density, it's a very tiny window. Okay, but there is a density in which you can consider the effective range to be much smaller than the internuclear separation density and the scattering length fairly large. So one can approximate neutron matter with that, but it works only in a tiny density regime. So in fact, if you want, this shows that you really need to account for the effective range if you want to have an accurate, but semi-realistic description of, unless you go to very, very low density. Okay, so here it's fine.
Go ahead. Since we have read brief also from your neural network, your policy that is quite powerful. It's you can get a high quality result from results and additional information. But how about you start from some? Since currently we have a shareholder function. Do you think if you can start with that kind of function, you may get accelerate of your? I'm not sure.
Yes. So the answer is so okay. There are people doing that, like DeepMind, for example, want to learn molecules, or they want to learn the wave function of complicated condensed matter systems, and you want to know that with chemical accuracy. Then it is critical to do a pre-training. So what they do, they maximize they do something different. They actually start from single particle orbitals obtained by Hartree-Fock, and then do a backflow transformation on them. Okay. In nuclear physics, we are not at that level of accuracy. So the uncertainty in the nuclear force typically dominates the uncertainty in solving the many-body Schrödinger equation. So I really like the self-emergence of shell structure and from scratch. But in principle, what you say is right. I mean, I could pre-train the wave function with a Hartree-Fock calculation, maximizing the overlap. Okay, so I can sample the Hartree-Fock wave from the Hartree-Fock wave function, maximize the overlap, and find the initial parameters of the net. And then start from there. That should accelerate the learning, yes. But I haven't done that just because we didn't do that just because we wanted to see self-emergence of cluster structure. But I mean, once we demonstrated that, if we want to do larger nuclei, saving a lot of time, we should do that.
Okay, explain more about your practice.
Yeah. So for example, let's see one of those wave functions. Let's see this one, for example. Okay. So there are there is a just row function, which is permutation invariant, and this is done through a deep set architecture. The idea is that we start from the single, forget about the message passing, okay? You start from the single particle coordinates of the nucleons, so x, y, z, and spin projection and isospin projection. You apply a fully connected neural network to this, the same network to all of them. And the network has, I don't know, 20-dimensional output. So you have 20-dimensional times the number of particles output, a matrix if you want. Then you sum over the particles. So you have rows and columns, and you sum over the rows. So you are left with 20-dimensional input, and that one is fed into another net, which is again fully connected. There is no fancy stuff going on. And that one gives us J. In the Fathian, instead, it is really a fully connected network that takes as input the 10 numbers. So the coordinates of nucleon 1, say, and nucleon 2, and that gives us this eta. And then we anti-symmetrize by hand. So we apply the same net to exchanging 1 and 2, the ordering, and then this gives us an anti-symmetric phi. The structure is, we try to keep the structure as simple as possible, and I can give you the details, but typically, say for, I don't know, silicon 34, sulfur 36, sorry, which is the largest nucleus we did with Hilbert plus GraphNet, we are talking about 50,000 variational parameters, which is a lot by conventional variational Monte Carlo, but it's nothing compared to like ChatGPT.
So, when you calculate your magnetic moments, I think this external field, okay, so this is like cranking. This is what we call cranking.
Yes.
In say high-speed physics. So you violate our reverse symmetry. So does it make any problems for you?
We turn it on. So we do that, and it does violate time reversal symmetry, but we don't impose it in the wave function. So for a while we don't care, but then when we actually, once we reach the size angular momentum value, we switch the external field off, and then it's when we measure the magnetic moment. So in fact, what happens? I wanted to show you this because I'm really fond of this thing. Actually, Antoine George said,
Do you have a name for that learning? Like induced learning?
I don't like giving names to stuff, like to my net, or giving names to dogs is a really difficult, and in fact, giving names to. Anyway, so this is the thing, right? I mean, here we actually overshoot J, but then by doing this imaginary time diffusion again, we filter out these excited state components. And I don't know why okay, we should plot this for longer because this is what we actually do. But anyway, the magnetic moments here then becomes stable. You can see
the system and then let it go.
Yes. But then, you know, if we wait long enough and there is noise in the metropolis, then eventually we can go back to a random state. But it happens like, you know, it's like I discovered recently the lead 208 is not stable against alpha particle emission. I didn't know that. I'm really ignorant. And yeah, and it's a similar thing. So it will eventually happen, but who knows when.
Sorry, we have ended the discussion here, but he will be here today and part of tomorrow. So if you want to talk to the speaker, sign up the meeting schedule. And also, if you want to go to dinner with speaker, just let me know. Yeah, thank you.